Hello everybody, today's going to be a special video because people keep asking me to do a how to build an e-bike battery pack video. So I'm going to take the battery that I spec'd out from the E2 e-bike video and build it. This video is going to be more technical than my other videos, so if you just want to see me rip some high power PEVs, then check out my other videos. Before I start building the battery pack, I'm going to give a quick explanation of how you determine what configuration of cells you want in your battery pack. If you already know about this, you can go ahead and skip this section. The cells I'm going to be using are 18650 cells. When you see this number, it really just tells you the size of the cell. 18 is 18 millimeters diameter, 65 is 65 millimeters length, and then the 0 at the end means it's a cylindrical cell. Because these cells are Li-ion cells or lithium-ion cells, their nominal voltage is 3.6 volts. This is kind of like the mid-range voltage that we base all our values on. The maximum voltage is 4.2 volts and the minimum voltage is 3.2 volts. However, the actual minimum is more like 2.5, but there's not a huge gain in draining your batteries that far, and it just makes them degrade faster, and there's a risk it'll go way under 2.5 if you just forget about it for a bit. So most of the time we treat it like the minimum is 3.2 volts. The storage voltage is 3.6 to 3.8. This keeps the battery kinda near this 3.6 and maybe a little above in case it drains a little bit. And this stops the battery from degrading and losing its capacity over time, which would happen if you had it at 4.2 volts or 2.5 volts for a long time. Next is the capacity of the cells. This really depends on what model of cell you have. Mine are EVE33V cells, which are 3.2 amp hours. This just means that this cell can output 3.2 amps for 1 hour, or it can output 1 amp for 3.2 hours. This is pretty good, as the highest capacity 18650s right now are about 3.6 amp hours. Finally, we have discharge current. This also heavily depends on what model cell you have. This cell is rated for 10 amps continuous, which means that as long as it stays cool enough, it can output 10 amps from full all the way to empty. 10 amps continuous isn't anything to brag about. The highest current cells can go up to 35 amps continuous. However, you can still make a great pack out of 10 amp continuous cells. When picking a cell, you can either pick a capacity cell or a power cell, and you can tell this is a capacity cell because it has not super crazy amps, but it has nearly the max amount of capacity. Now it's time to connect the cells together. The first connection to know about is a parallel connection. This is where you connect the two positives and two negatives together, just like this. This gives you 2 times the capacity and 2 times the discharge current, and this does not affect your voltage at all. The other way to connect cells is a series connection. You do this by putting the positive of one cell into the negative of another. This gives you 2 times the voltage, but does not affect the discharge current or the capacity. Both the series and parallel connections are abbreviated together with S and P. So this would be a 2S 1P for 2 series 1 parallel, while this one would be a 1S 2P for 1 series 2 parallel. Here's an example of using both the series and parallel connections. This is a 3S 4P pack, which means compared to a single cell it has 3 times the voltage, 4 times the capacity, and 4 times the discharge current. Now, going back to our original 2 packs, this pack can be used fine like this, since these cells are basically just acting as one big cell. However, using this pack like this can cause some problems. By connecting cells in series, you just unlocked a new problem, which is cells becoming unbalanced. If you had 2 cells connected like this and you just kept charging and discharging them, eventually one of the cells is going to have higher voltage than the other one. This is a problem on discharging because the lower voltage cell might go under 2.5 volts and get ruined. It's a problem on charging because the higher voltage cell might go over 4.2 volts and burst into flames. There's 2 ways to solve this problem. The first way is to have one main power connector on the pack that connects from the main negative to the main positive and does most of the current for charging. And then you have a second little connector that connects to every different voltage point on the pack. This way the charger can manage the voltage of every cell individually and charge them all to the exact same voltage. This is common for smaller battery packs that you want to keep as cheap and simple as possible. The second way to solve this problem, and what I'm going to do for this pack, is to have a BMS. BMS stands for Battery Management System. It's a little circuit board that goes inside your battery, and it connects to the positive and negative terminal of every cell to make sure they're always balanced perfectly. Because the main battery minus goes through the battery minus port and out the charge minus port, the BMS has the ability to cut power if anything bad happens, such as if the temperature sensors read the battery is too hot or too cold, or if the balance gets way off, or if the battery gets too high charge or too low charge. There's two types of BMS, a smart BMS and a dumb BMS. A dumb BMS comes from the factory with all the voltage, current, and temperature values set, and you can't change them. A smart BMS lets you connect to the BMS with your phone to change all those values to whatever you want. It also lets you read the voltage of each cell individually to make sure that your whole pack is perfectly balanced. The smart BMS really isn't that much more expensive than a dumb BMS, so of course I'm going to be using a smart BMS. With all that being said, how am I going to determine what series and parallel connections I'm going to use for this pack? Well, I've already decided on 20S because that's 72 volts nominal, which is the standard for high-power e-bikes, and it's really good for these far driver controllers because it's the maximum amount that these smaller controllers can do. If I wanted to go to a higher voltage, I would have to go all the way down here to a 96450 controller, and that's $300 and 16,000 watts, so it's a bit more power than I need for most of these smaller builds that I like to do. For the number of cells in parallel, I can only fit 10, so that's what I'm going to do. So here's the diagram for the battery. Like I said earlier, it's going to be a 20S 10P battery. 20 series means it'll be 72 volt nominal, 64 volt minimum, 84 volt maximum with a 72 to 76 volt storage. 10 parallel means it'll be a 100 amp continuous discharge with 32 amp hours of capacity. It seems a bit complicated at first, but it really isn't. All these purple wires are just the balance wires, going from 1, 2, 3, 4, 5, 6, and all the way up. Then you got some temperature sensors, and then the main power wires, and that's about it. One thing to note on BMSs is that they only say the series number, they don't say anything about parallel. And this is because when you add more cells in parallel, it's the same voltage, so the BMS doesn't really care. Alright, now it's time to start building. Here's one of the cells I'm going to use. There's the positive end and then the negative end. This wrapping around the cell is really important because if you remove it a little bit, you can see the negative end of the cell actually is the entire cell up to here. So that means the positive end and the negative end are right next to each other. So if you had a totally bare cell, it would be super easy to short. Next are the spacers. I'm going to be using these offset cell spacers. They're sometimes called honeycomb or dislocation spacers. They snap together really easily. And these spacers are good because they don't waste as much space in the battery compared to the older style of spacers, which is just a grid like this. As you can see, between each set of 4 cells, there's a spot that's just wasted space. Using spacers like this is nice because you get a nice rectangle shape, but I don't think it's worth having a bigger pack. To connect the cells, people often use nickel strips and spot weld them on just like this, and then go back and put them on the other way, like this. However, this isn't the best way to do this, as you end up with a bunch of spot welds everywhere that could fail. The much better way to connect the cells, which I'm going to do, is to use these dislocation spacers and then this pre-cut nickel that's cut to go perfectly on these spacers, just like this. If you do this, the nickel and the spacers are going in opposite orientations, which makes the pack super strong. Here's how the cells look in the spacers. You can see they have a little gap in between them. This makes sure they will absolutely never short out. Some people don't even use spacers, but in my opinion that's a bad idea, because the cells are right on each other, and this thin wrap might wear through with some vibration, and then your whole battery is shorted out. For the BMS, I went with an Ant Smart BMS that can do 100 amps continuous and 250 amps peak. The BMS can do 17 series all the way up to 24 series. The BMS also came with balance wires and temperature sensors, and of course the manual. All the cells are ready to go in the pack, but before I put them in, I need to determine what orientation would be best. If I put the BMS on top, that means I have to have the current start here, go down the pack, and then come back up the other side. I decided that the best thing to do would be to have the battery minus connect to the inside of this row of cells and have it zigzag down the pack. That way I can connect the inside of the left side to the inside of the right side on the bottom. This also puts the main positive up here next to the main negative on the BMS, which makes adding the connector really easy. After determining the layout, I cut the pre-cut nickel into the right size, leaving this little extra bit on the end for the balance wires to connect. I chose to do the balance wires on this side because they plug into the BMS at the top of this side, so it should make it pretty easy. After this, I put all the cells into the spacers. If they don't go in all the way, you can gently tap them with a rubber mallet to get the spacers to fully lock in. Now this is starting to look like a battery pack. Time to do one last check to make sure I put all the cells in the right positions. At this point, you can cut out some plastic sheets to put on the sides of the pack and in the middle of the pack to separate the two halves. Now it's time to start spot welding, but first I need to do what's called a tear test. I start by grabbing this extra cell that I accidentally pulled a hole in the negative terminal so I can't use it. At first that may look like a good spot weld, the nickel's stuck to it, but it's actually not. It comes right off with a little bit of force. You can tell the spot weld was not powerful enough because no nickel was torn off and left on the terminal of the battery. Now it's time to turn the power up on the spot welder and try it again. I can tell it's more powerful now because it shoots off a couple sparks. The result looks pretty much the same, but it's an actual weld now. As you can see, there's two holes straight through the nickel. And on the battery cell, you can see two little bits of nickel stuck to it. There's actually two other spots, but that's from the old spot welds when I salvaged these cells. I've started the spot welding process. What I like to do is spot weld one side, just like that, and then put a little magnet on the other side to hold the nickel in place. I then go along spot welding just like this. What some people like to do is spot weld the ends and then finish off the middle, but that leaves a bunch of extra material in the middle, which makes spot welding a bit harder. So I like to start on one side and go along like that, which really flattens it out. For these cells in particular, since I salvaged them, there's these two little spots I can't spot weld to, so on the negative terminal I just go really wide on the middle spot weld. I also do 3 instead of 2. Depending on your setup, the nickel might want to spring up a little bit just like this. So what I like to do is take one side of the spot welder and just bend them down a little bit just like this. Now that I spot welded the nickel on the outside of both halves of the pack, it's time to stand them back up to make sure I did it all right. Notice all the balance wire connection points are on the correct side, and I even bent them in to get ready to solder the wires. At this point, you still cannot short any of the cells out on the outside halves of the pack because there's no connections on the inside, but this is where it gets tricky. If you weren't paying attention and you laid the nickel on just like that, it would short out the top 2 rows of cells. So you have to make sure you don't put the nickel like that, but you offset it by 1 there to connect the top 4 rows of cells. Once you have all that done, it's time to think about the main power wires. This is a strategy that I've used before. It's pretty self-explanatory. To make sure I get good spot welds, I cut a little slit out of all the nickel strips. After that, you can put the 2 halves of the battery end to end and start arranging everything to get ready to spot weld. I cut out some strips like this to bridge the middle section. When soldering the nickel to the main positive and negative wires, you can also include a small auxiliary wire for the BMS. One thing to consider before spot welding is how the current will flow. The current is trying to get from this point over to this point. So the shortest path would be to go through the top row of cells, so these cells are going to get super stressed. Meanwhile, the bottom row of cells will have barely any current flowing through it. The solution is to flip one of the main power wires just like this. That way this path is the same distance as this path, and the whole pack should drain perfectly evenly. Here's the pack with all the spot welding finished. Make sure you add some fish paper before you bend the nickel strips over. I also should mention you really only need one parallel nickel strip in the middle section. Time to fold the pack. Make sure you put your plastic sheet in the middle, otherwise you're going to have a spark show. What I'm doing here is making sure it's perfectly aligned before I really squish it down, because squishing it down bends the nickel on the bottom and really locks it in position. I decided to put one little wrap of tape around the top of the pack just to make sure it all stays together. However, at this point I realized I messed up because I should have had the main positive and negative wires bent when I soldered them, so now I'll have to fix it. All I need to do is just melt that one spot and bend it. I should mention that when you're soldering wires this thick, you really need a powerful soldering iron, like 100 watts. Here's the BMS. I removed the wires it came with and soldered one negative wire on. Now obviously you don't want to just set it on top because that'll short it out, so we're going to have to put something here to separate it. Here's what I came up with. It's some foam, double-sided tape, and more fish paper. I also put a little bit of foam on top of the wires just to hold them down to stop them from moving. Well, I made yet another mistake. I forgot about the temperature sensors. I like to do this strategy where I cut some slits out in the middle separating plastic piece so I could put the sensors at the perfect places to sense the hottest parts of the battery. So I pulled the center sheet out and replaced it with a piece of cardboard to make sure the battery doesn't short, and now I can cut the slits. The temperature sensor wires were too long, so I had to cut them down. Here they are plugged into the BMS. Now it's time to solder the balance wires, but before you do that, you need to look at the diagram that the BMS came with. To configure the balance wires for a 20S battery, we need to cut the 3rd, 4th, and 5th wires from the left and connect the 1st, 2nd, and 6th wires all together. Doing this now will simplify things a lot later. The next step would be to get the battery in a good position where you have access to all the balance wire connections. After that, you want to tape the wires really close to where they'll plug in. You really don't want to solder them with them plugged in because you have all these loose ends everywhere that can easily short out and destroy your BMS. What I like to do is lay a layer of fish paper down and then poke a hole through the fish paper and run the wires under the fish paper. It gives a really clean look and no wires are overlapping. After that's done, you can solder the main negative wire to the BMS. But before you plug all your balance wires into the BMS, you need to go through with a multimeter and make sure they're all connected correctly. These plugs can be pretty annoying since they're so wide, but you just gotta keep pushing until you hear the little latch click in place. At last, you have a fully functioning battery. You can connect your charger to the main power wires with some alligator clips to start charging. On the Ant BMS app, you can connect to the Ant-BLE device, and then scroll down to make sure your temperature sensors are reading correctly and all your voltages look right. To make the battery pack actually work, you want to click this parameter set button at the bottom, and then come up and click Fast Setting. Click the lithium ion option, and then enter 20 in the unit number, and press Settings to save it. For physical C, we want to type the capacity, which is 32 for this battery. Click Settings again, and then to save this whole page, you have to click Save up at the top. Now if we return to the main page, we can see in the warning info section, charge MOS on and discharge MOS on, which means the battery pack is working. Now when you connect a charger, you can see the current and power values change. If you want to change your voltage settings, click vparams. Now you have all these settings to change, but don't change anything if you don't know what you're doing. What I like to do is turn unit over volt protect and unit over volt recover down a little bit for safety. To change your current settings, click current parameters. I had to change my discharge overcurrent protect to 100 amps because that's what my cells can take. I also had to turn my charge overcurrent protect to 30 amps since each of my cells can charge at 3 amps. There's also another app I like to use called BMS Tool. You can connect to many different kinds of BMSs, you can connect to multiple at the same time, you can see the temperature in Fahrenheit, and you can see a visual representation of the cell's voltage. Now that you know the battery works, it's time to tape it up with Kapton tape. I bought this 200mm roll of tape so I could do whole sides of the battery at once. It's kinda hard to use, but it gives a good result. I start by doing one like that, then one like that, and then do it again. For the top section, I use the smaller rolls of tape. Next is the fish paper, and just like the Kapton tape, I got a really wide roll so I could do the entire side at once. It helps to cut some little cutouts on the ends like that on any rounded parts so you can fold it nice and flat. I put the fish paper on the same way I put the Kapton tape on. Now to protect the corners, I'm going to add a couple layers of electrical tape. After the electrical tape and some more Kapton tape, it's time to shrink wrap. To go in this direction, you want to measure it out like this. As you see, I have some extra, which is good. Now, for the other direction, you want to measure it out like this. That's not enough extra, so I'm going to have to get this slightly wider roll. Here's how I'm going to do the first shrink wrap. You're going to have some extra on the ends because it will shrink in a bit. This is more than enough on the ends, but this is all I had left, so I might as well use it all. After you let it cool for a bit, you can cut off the ends with the razor blade, trying to keep only the flat part. For the other direction, I judged the amount I needed almost perfectly, which was nice, but the seam split open here, which is annoying, because I don't have any more of this size left. I think I'm going to be able to salvage it though, with some hot glue. I ended up filling the holes with hot glue, and then putting the backing paper from some fish paper on it, and then putting some heavy stuff on it to really compact it down, and I think it turned out waterproof. I also did the rest of the seams, so this battery should be super water resistant. Now it's time to solder on the main discharge connector. You want to have your wires be the same length, so you want to cut them. But you don't want to do that because you can see it'll short out right there. So you want to get in the right position and then move the wire out of the way and cut it. Before we actually solder on the main discharge connector, we need to do the charging connector. I like to use an XT60 and use the wires that I just took off the BMS. By this point, I've soldered so many of these XT60 connectors I can get them nearly perfect every time. A good tip is to have the connector plugged into another connector like this, so it holds it all steady. Once I put on this piece, it should be perfect. Here's my setup for soldering on a QS8 connector. I like these connectors as they have a built-in anti-spark resistor. Once again, you're going to have to use a powerful soldering iron. Sadly, I couldn't use the plastic cover on this connector, so I just shrink wrapped it, but there's still a little gap there, so I'm just going to wrap it with some electrical tape. Once I wrap that, the battery is done. To give you a comparison to a battery you could buy instead of making this battery, I have this BTR Power 72V 30 amp hour battery. As you can see, it's significantly larger and heavier than my battery with the lower capacity. I couldn't find this exact battery, but I found the 20 amp hour version, which is $439. So if you increase that price by 50% to get the price of the 30 amp hour version, it's still more than double the cost of my battery plus a charger. The 30 amp hour battery would have a 75 amp BMS, which is less current than my battery. Also, the battery only has a dumb BMS, so I think my battery is really better in every way. To test the battery, I put it in my Ego mini bike, fully charged it, and rode it till it was totally dead, and it worked perfectly. If you haven't seen the video about this bike, you should check it out, it's a beast. I also tried the battery in my next build, and it worked pretty good. It definitely needs more power, but I'm working on that. That's it for this video. I hope you guys learned something new about building battery packs. If you want to know more, there's plenty of other videos out there, plus you can ask me some questions in my comments or on my Discord. Anyways, thanks for watching.